Space, for most of human history, existed only as a distant canvas, a night sky scattered with stars, planets, and mysteries. Ancient civilizations gazed upward, charting the movements of celestial bodies out of curiosity, reverence, and the need to measure time or navigate the seas. Yet the idea of venturing beyond Earth's atmosphere remained the stuff of imagination until the 20th century, when rapid advances in science and engineering transformed fantasy into reality. What began as a noble quest for knowledge and discovery would, over the decades, reveal space as more than just a scientific frontier. It would become a strategic domain, a stage for technological rivalry and national security interests. To understand how space became a warfighting domain, it is essential first to consider its physical nature. The boundary between Earth and outer space is commonly defined as beginning at 100 kilometers above sea level, or roughly 62 miles. This line, known as the Kármán line, marks the point where conventional aircraft can no longer operate effectively and where the true expanse of space begins. Space itself presents an environment unlike any on Earth. There is no air to breathe or carry sound, no atmospheric pressure, and temperatures can swing dramatically between sunlit and shadowed areas. These harsh conditions demand extraordinary technological solutions for life support, propulsion, and communication solutions that have continually pushed the limits of human ingenuity. The drive to overcome these challenges led to some of the most remarkable achievements of the 20th century. The mid-1950s marked the dawn of the so-called space race, a period defined by intense competition between the United States and the Soviet Union. This rivalry was rooted in the broader context of the Cold War, a struggle for global influence that extended from the surface of the Earth into the stars above. The launch of Sputnik 1 by the Soviet Union in 1957 was a watershed moment. This small, beeping satellite was the first human-made object to enter Earth's orbit, and its successful deployment demonstrated not only scientific prowess, but also the dual-use potential of rocket technology. The very rockets that could propel satellites and astronauts into space could also deliver intercontinental ballistic missiles, blurring the line between peaceful exploration and military capability. The United States responded swiftly. In early 1958, the launch of Explorer 1 marked America's entry into the space age. That same year, the National Aeronautics and Space Administration, or NASA, was established to coordinate the nation's civilian space efforts. Yet even as NASA championed exploration and discovery, the military dimensions of space were never far from view. The technologies enabling humans to explore space, powerful rockets, precise guidance systems, and remote sensing instruments were inextricably linked to national security. Both superpowers recognized that dominance in space could confer significant strategic advantages on Earth. The early milestones of human spaceflight further underscored the dual nature of space activity. On April 12, 1961, Yuri Gagarin became the first human to travel into space, completing a single orbit of Earth aboard a Soviet spacecraft. Just weeks later, Alan Shepard became the first American to fly into space, and on February 20, 1962, John Glenn made history as the first American to orbit the planet. These achievements captured the world's imagination and were celebrated as triumphs of human spirit and ingenuity. Yet beneath the surface, they were also demonstrations of technological capability, with implications for military applications. As the 1960s progressed, the space race accelerated. The United States and the Soviet Union each sought to outdo the other with increasingly ambitious missions. The Apollo program, culminating in the first human landing on the moon, required a host of technological innovations, from powerful Saturn V rockets to sophisticated life support systems. Many of these advances found applications beyond exploration, shaping the development of communications, surveillance, and navigation systems that would become essential to modern military operations. This period also saw the introduction of international agreements intended to guide the use of space. In 1967, the Outer Space Treaty was signed, establishing the foundational legal framework for activities beyond Earth's atmosphere. The treaty enshrined the principle that space should be used for peaceful purposes, prohibiting the placement of nuclear weapons and other weapons of mass destruction in orbit or on celestial bodies. It also emphasized the importance of international cooperation and the idea that outer space, including the moon and other celestial bodies, would be free for exploration and use by all countries. This treaty, adopted by the United Nations General Assembly, remains the cornerstone of space law. While it set important boundaries, it did not eliminate the potential for military activity in space. The treaty specifically prohibits weapons of mass destruction, but other military uses, such as reconnaissance, communications, and early warning systems, were not explicitly banned. As technologies matured, the military value of space-based assets became increasingly apparent. Satellites provided unprecedented capabilities for gathering intelligence, monitoring potential adversaries, and enabling secure communications over great distances. The development of remote sensing technologies allowed nations to observe activities on the ground with remarkable detail, fundamentally altering the nature of surveillance and reconnaissance. The same rockets that launched scientific missions could be adapted for military purposes, highlighting the persistent dual-use character of space technology. The emergence of space as a strategic frontier continued into the late 20th and early 21st centuries. The growth of the commercial space industry brought new actors and capabilities into orbit. With the proliferation of satellite launches, space became increasingly congested, raising concerns about sustainability and the risks posed by orbital debris. The so-called space sustainability paradox emerged. While space-enabled technologies offer enormous benefits for life on Earth, supporting everything from global communications to environmental monitoring, the sheer volume of activity increases the risk of collisions and the creation of hazardous debris. Many of the laws and norms governing space activities, established decades earlier, have struggled to keep pace with these rapid changes. Recent decades have also witnessed renewed interest in the outer reaches of Earth's neighborhood. The Artemis program, for example, represents an ambitious international collaboration aimed at returning humans to the Moon and establishing a sustained presence there. Advances in propulsion, robotics, and life support are enabling missions to cislunar space, the region between Earth and the Moon and beyond. Some analysts refer to regions like X-GEO and cislunar space as space frontier areas, noting that while missions there are increasing, they have not yet reached the scale to form fully established domains. Nonetheless, the trend is clear. The physical and technical boundaries of human activity in space are expanding, bringing new challenges and strategic considerations. Amid these developments, the establishment of dedicated military organizations for space has become a notable feature of the modern landscape. The United States traces the origins of its Space Force back to 1958, when the launch of Explorer 1 signaled a national commitment to both exploration and security in the new domain. Over time, this commitment has evolved, with space now recognized as a critical arena for national defense, economic prosperity, and international competition. Yet, despite these shifts, the foundational vision of space as a realm for peaceful exploration endures. The Outer Space Treaty and subsequent agreements reflect a shared aspiration to prevent the weaponization of space and to ensure that its benefits are available to all humanity. However, the realities of technological advancement and geopolitical rivalry continue to test this vision. The dual-use nature of key technologies means that lines between civilian, commercial, and military activities are often blurred. The global community faces ongoing challenges in developing new norms, regulations, and cooperative mechanisms to address issues ranging from security and sustainability to access and equity. Looking back over the decades since the first artificial satellite was launched, it is clear that space has evolved from a distant dream to an integral part of human affairs. The journey has been shaped by scientific curiosity, technological innovation, and strategic competition. The physical characteristics of space, its vastness, its hazards, its unforgiving environment, have demanded new ways of thinking and problem-solving. The early milestones of exploration, while celebrated for their spirit of adventure, also set the stage for the militarization of the domain. International agreements have sought to keep space peaceful, yet the pressures of national security and economic interest remain ever present. Today, the story of space as a warfighting domain is still being written. The interplay of exploration and competition, of cooperation and rivalry, continues to define the trajectory of human activity beyond Earth. As technology advances and more actors enter the space arena, the challenges of sustainability, security, and governance will only grow in complexity. But the foundations laid by the pioneers of exploration, the architects of treaties, and the innovators of science and engineering endure, shaping the future of space as both a frontier of discovery and a strategic domain. In this evolving landscape, the choices made by nations and the international community will determine whether space remains a realm of possibility and promise or becomes a new arena for conflict and contest. In the hush of night, when you look up at the stars, what you cannot see, the invisible threads of radio waves, the silent passage of satellites, the constant hum of digital traffic is just as important as what dazzles your eyes. Modern militaries now depend on this unseen web encircling our planet. Space is no longer simply a theater for exploration or a quiet backdrop for scientific observation. It is recognized as a warfighting domain where technological mastery brings real-world advantages. The science and engineering driving this transformation are both subtle and staggering, blending cutting-edge physics with the relentless demands of national defense. At the heart of military activity in space are satellites, those unassuming machines orbiting hundreds or thousands of kilometers above us. Their design is a careful balance of mass, power, and precision. Military satellites are built to withstand the harsh conditions of orbit, extreme temperatures, radiation, and the ever-present threat of space debris. To function reliably, these machines combine highly efficient solar panels, lightweight materials, and resilient electronics. Small satellites, in particular, have captured the attention of both civil and military programs. Their compact size and lower cost make them ideal for rapid deployment, experimentation, and redundancy. As a result, constellations of small satellites are proliferating, each one a node in a vast, flexible network that can adapt to shifting operational needs. Satellites serve many roles in defense, but perhaps the most fundamental is communication. Modern warfare demands instant connectivity, commanders coordinating troops, pilots updating mission plans, unmanned systems relaying sensor data from distant frontiers. This need has driven the evolution of military satellite communications, or SATCOM, into a complex and ever-advancing field. Early systems relied on bent pipe transponders, which simply relayed signals from one ground station to another. Today, regenerative processors on board can filter, clean, and even encrypt data before sending it back to Earth. Cross-link capabilities allow satellites to communicate directly with each other, forming a mesh of communication pathways that are less vulnerable to disruption. Security is paramount. Military satellites often operate across multiple frequency bands, such as X-band, Ka-band, and beyond, balancing the need for high data rates with resilience against jamming and interception. The Lincoln Experimental Satellite 9, for example, pioneered the use of Ka-band, opening new possibilities for resilient, high-capacity communication. Advances in radio frequency engineering have also brought innovations like electronically steered beams, which can shift focus in microseconds, and sophisticated modulation techniques that pack more information into every hertz of bandwidth. Optical communication using lasers instead of radio waves promises even greater capacity and resistance to interference, though it introduces its own technical challenges. But connectivity is only part of the story. Satellites are also the eyes and ears of the military in space. Space-based sensors provide persistent all-domain awareness, the ability to track the position and behavior of objects across the globe day and night through cloud and darkness. These sensors take many forms: optical cameras that peer at the Earth's surface, radar systems capable of detecting movement through clouds, and infrared detectors that spot the heat signatures of missiles or vehicles. The fusion of these data streams gives military planners a dynamic, real-time picture of the battlefield. The importance of this persistent awareness cannot be overstated. Space sensors are vital for command and control, navigation, intelligence, surveillance, and reconnaissance. They inform nearly every step of mission planning and execution, from tracking adversaries' troop movements to monitoring the health of one's own assets. Without these eyes in the sky, decision-makers will be left guessing, operating in a fog of uncertainty. This picture of the battlefield, however, extends beyond the Earth below. Space itself is becoming increasingly congested and contested. The arena is crowded with commercial satellites, debris from past missions, and the growing fleets of small satellites launched by governments and private industry alike. Space Situational Awareness, or SSA, has emerged as a discipline in its own right. SSA is best described as predictive knowledge of resident space objects and the operational environment. It requires not only tracking the location and trajectory of thousands of satellites and fragments, but also predicting close approaches or conjunctions before they become collisions. When a potential risk is identified, operators must be warned in time to maneuver their satellites to safety. The tools that enable SSA are as diverse as they are sophisticated. Ground-based telescopes and radar stations scan the heavens, cataloging and monitoring objects in orbit. Space-based sensors add to this picture, offering vantage points that ground stations cannot match. Advanced algorithms sift through torrents of data, seeking patterns, predicting threats, and enabling real-time decision-making. For military operators, SSA is indispensable. It allows them to mitigate risks, plan missions with confidence, and maintain the operational effectiveness of their space-based assets. The intertwining of civilian and military interests is perhaps nowhere more apparent than in the realm of satellite navigation. The Global Positioning System, or GPS, stands as a testament to the dual-use nature of space technology. developed originally for military purposes, to provide precise location and timing data for everything from aircraft navigation to missile targeting. GPS has since become a backbone of the global economy. Its signals synchronize financial networks, guide ships at sea, and underpin countless civilian technologies. This blending of civilian and defense applications is echoed in many domains. Weather forecasting, climate monitoring, telecommunications, and navigation all rely on space-based systems first developed for or adopted by the military. Such dual-use technologies introduce both opportunities and challenges. On one hand, they accelerate innovation, as breakthroughs in one sector spill over to benefit the other. NASA's technology development, for example, has yielded spin-offs that touch countless aspects of daily life. Memory foam, scratch-resistant lenses, and even invisible braces have their roots in the demands of space exploration. On the other hand, the line between civilian and military applications is becoming increasingly blurred. Civilian satellites equipped with artificial intelligence can now perform military functions such as surveillance or secure communications. This raises difficult questions about governance, regulation, and the risks of escalation in times of crisis. The relationship between government and industry has also evolved. The transformation of military satellite operations increasingly relies on collaboration between the public and private sectors. Government agencies partner with commercial firms to harness the latest innovations, improve resilience, and integrate commercial solutions into defense architectures. The partnership between companies like Viasat and branches of the military, for instance, has enabled more robust, flexible, and secure SATCOM capabilities for deployed forces. The integration of commercial technologies is not just about cost savings, it brings agility, rapid iteration, and access to a broader pool of technical expertise. Engineering the satellites themselves has become a science of optimization. Every gram of mass must be justified, every watt of power carefully allocated. The systems engineering process for small satellites, now a focus for both civilian and military programs, weighs trade-offs between payload capacity, survivability, and cost. The proliferation of small satellites in low Earth orbit is reshaping the architecture of military space operations. Rather than relying on a handful of large, expensive satellites, modern constellations are designed for redundancy and resilience. If one node is lost, others can take its place, reducing vulnerability and increasing flexibility. What trends are shaping the future of space as a warfighting domain? Experts highlight the rapid adoption of artificial intelligence and machine learning for on-orbit operations. These technologies promise to automate routine tasks, optimize data collection, and even enable satellites to respond autonomously to threats or changes in the environment. Quantum communication is another area of intense interest, holding out the possibility of fundamentally secure links resistant to interception or eavesdropping. The growing convergence of satellite and telecommunications industries is blurring traditional boundaries, with direct-to-device satellite services inching closer to reality. The space economy is booming, projected to reach $1.8 trillion by 2035. This growth is driven not only by defense spending, but by the expanding role of space technology in daily life. Weather forecasting, navigation, global communications, these civilian applications are deeply intertwined with military priorities. The same satellites that track hurricanes or enable internet access in remote areas can also support military operations, provide strategic warning, or enhance situational awareness. As more countries and commercial actors enter space, the regulatory landscape grows ever more complex. The distinction between civilian and military systems is eroding, and the challenge of defining and governing dual-use technologies is becoming sharper. Artificial intelligence, cybersecurity, and green energy solutions are all areas where the interests of defense and civilian sectors intersect, sometimes in unexpected ways. The result is a domain where innovation is rapid, competition is fierce, and the stakes for security, prosperity, and even the safety of the planet are growing higher. Space, once the province of dreamers and explorers, is now a realm where science, engineering, and strategy converge. The invisible infrastructure orbiting high above us is a testament to human ingenuity and a reminder that the struggle for advantage in this new domain is as much about algorithms and antennas as it is about rockets and ambition. In this shifting landscape, the interplay between civilian and defense applications is not just a matter of convenience. It is a defining feature of the modern age, shaping the way nations plan, act, and defend their interests on the ultimate high ground. Space is no longer the untouched expanse once romanticized as a sanctuary for peaceful exploration. Instead, it has become a domain marked by competition, conflict, and vulnerability. A new frontier where the rules are only partially written and where the balance of power on Earth increasingly depends on who can secure the high ground above. The very satellites that connect global communications, direct military maneuvers, and monitor weather patterns are now seen as both vital assets and tempting targets. Major powers have made it clear, space is a warfighting domain, and the ability to shape outcomes in orbit is inseparable from national security on the ground. At the center of this transformation lies a paradox. Space is governed by a patchwork of treaties and legal frameworks intended to prevent its weaponization, yet the technologies and tactics evolving in orbit rarely fit neatly within those boundaries. The Outer Space Treaty, for example, bans the placement of nuclear weapons in orbit, but says little about other means of contesting or disabling space systems. As a result, military planners and diplomats find themselves operating in a gray zone, where the spirit of international law often lags behind the realities of technology and strategy. The vulnerabilities are stark and growing. Satellites once thought invulnerable due to their remoteness are now within reach of a range of counterspace capabilities. Direct-Ascent Anti-Satellite Weapons, or ASATs, have been tested by several nations. These missiles, launched from Earth, can reach and destroy satellites in low orbits. The consequences of such actions ripple far beyond the initial impact. Debris from a single strike can clutter orbital lanes for decades, threatening not just military systems, but the global infrastructure that depends on space. Experts warn of a cascading effect, known as the Kessler syndrome, in which debris from one collision triggers further collisions, rendering vital orbits unusable for all. Not all threats are so dramatic or visible. Co-orbital systems, spacecraft designed to maneuver close to other satellites, can shadow, inspect, or potentially interfere with their targets. The intent behind such maneuvers is often ambiguous, blurring the line between peaceful inspection and hostile action. Electronic warfare adds another layer of complexity. Jamming and spoofing signals can disrupt satellite operations without leaving physical traces, making attribution and response deeply challenging. Perhaps the most insidious risks unfold in silence, through the invisible realm of cyberspace. The computers, networks, and ground stations that control space assets are increasingly under siege. Recent years have seen a rise in cyber incidents targeting satellite infrastructure, with attackers aiming to disrupt military operations, steal sensitive data, or sow confusion. The interconnectedness of space and terrestrial systems means that a vulnerability in one can cascade into the other, amplifying the potential impact. Experts stress that cybersecurity must be built into space systems from the ground up, with robust governance and accountability throughout the supply chain. The scale and diversity of these threats have prompted a re-evaluation of resilience in space architecture. It is no longer sufficient to rely on hardening a handful of critical satellites. Instead, defense planners emphasize disaggregation, spreading capabilities across multiple satellites or even constellations to reduce the risk posed by any single failure. This approach, however, brings its own challenges, including the need to balance military resilience with the safety and integrity of civilian infrastructure that often shares the same orbits. International organizations and alliances are adapting as well. NATO, for example, has developed an overarching policy framework for space, emphasizing the need for collective security and deeper cooperation among allies. This approach recognizes that no single country can unilaterally secure the space domain. Joint capabilities and information sharing are seen as essential tools for deterring aggression and managing the risks of escalation. According to many analysts, the strategic advantage in space now depends on both technology and partnership. Yet, even as nations scramble to defend their interests, they must navigate a legal and ethical minefield. The use of anti-satellite weapons, for instance, raises difficult questions of proportionality and self-defense. The prospect of generating debris that could endanger all users of space weighs heavily in legal and policy debates. International humanitarian law, which governs conduct in armed conflict, has only begun to be harmonized with the unique challenges of space operations. Many scholars argue that existing treaties are ill-equipped to address emerging technologies such as co-orbital systems, cyber weapons, and directed energy devices. Meanwhile, the global counterspace capabilities landscape is evolving rapidly. The 2024 Global Counterspace Capabilities Report details a wide array of tools now in development or operation around the world. These range from traditional direct-ascent missiles to electronic warfare systems and sophisticated cyber tools. Notably, the proliferation of such capabilities is not limited to the most powerful states. A growing number of countries and non-state actors are acquiring the means to contest space, often by exploiting commercial technologies with dual-use potential. This democratization of counterspace power raises the stakes for governance and transparency. As more actors enter the domain, the risks of miscalculation, accidental escalation, or deliberate provocation multiply. The international community faces a daunting task: how to update norms and agreements to reflect new realities without stifling innovation or unduly restricting access. Some proposals focus on transparency measures, such as notifications of satellite launches or maneuvers. Others call for clear definitions of what constitutes hostile or irresponsible behavior in orbit. The specter of nuclear-armed space weapons, while largely constrained by existing treaties, has not disappeared entirely. Analysts warn of the risks posed by the erosion of long-standing norms, particularly if rivalries intensify or new technologies outpace the ability of diplomats to respond. Preventing a new arms race in space is widely seen as both urgent and challenging, demanding a level of trust and verification that is not easily achieved. Even as these debates continue, the practical demands of defending space assets are mounting. Missile warning and reconnaissance satellites are now regarded as indispensable for national security, providing early detection of threats and supporting the command and control of military forces. Their importance makes them prime targets, and their defense a top priority for policymakers. Strategies to protect these systems include hardening against physical and electronic attack, deploying redundant platforms, and developing rapid replacement capabilities. Cyber resilience is central to these efforts. The range of potential attack vectors is broad, encompassing everything from software vulnerabilities and supply chain compromises to insider threats and social engineering. Experts highlight the importance of embedding security into the design phase of space systems, rather than relying on fixes after vulnerabilities are discovered. Enhancing cyber situational awareness, knowing not just where the satellites are, but how healthy and secure their systems remain, is now considered a core competency for modern space operations. The interplay between civilian and military space infrastructure adds another layer of complexity. Many of the systems that underpin daily life, navigation, financial transactions, weather forecasting, depend on satellites that are also of military interest. The growing vulnerability of this critical infrastructure has prompted calls for improved legal, regulatory, and security frameworks. Ensuring resilience in the face of diverse threats is not simply a military concern, but a societal imperative. All these challenges are compounded by the sheer congestion of space. The pace of satellite launches is accelerating, driven by commercial ambitions as well as military needs. As orbital highways become more crowded, the risk of accidental collisions grows, further complicating efforts to distinguish between hostile acts and simple misfortune. The sustainability paradox, where the very success of space-enabled technologies increases the risks of congestion and debris, has become a defining dilemma for the era. Looking to the future, trends point toward continued innovation and rising competition. The potential for orbital global strike, the strategic use of maneuverable satellites, and the integration of artificial intelligence into space operations are all on the horizon. The imperative for responsible stewardship balancing security, sustainability, and equitable access has never been greater. Yet for all the sophistication of new technologies and the complexity of emerging threats, the enduring challenge remains one of governance and cooperation. No nation, however powerful, can secure the final frontier alone. The risks of conflict, miscalculation, and irreversible damage are simply too great. The pursuit of resilience, transparency, and collective security will define the next chapter in humanity's relationship with space. Whether space remains a domain of promise or becomes a theater of persistent peril depends on choices made not just by generals and engineers, but by diplomats, policymakers, and the broader global community. As the world contemplates the future of space as a warfighting domain, the stakes are clear. The assets in orbit are more than tools of power. They are the backbone of modern life and the foundation of global prosperity. Protecting them, while preserving the ideals of peaceful exploration and shared benefit, will require ingenuity, vigilance, and above all, a renewed commitment to responsible stewardship of the ultimate high ground.